The Large Hadron Collider tells us what our universe was like, or at least what the laws of physics were like a trillionth of a second after the Big Bang. I want to know what it was like 1,000 or 1,000,000 or 1,000,000,000 times before that. What about our universe's beginning are we really getting wrong?
Here we are in the august surroundings of the Royal Institution in London.
I've never been to the Royal Institution, but so many great figures have walked these halls and given talks here. It's pretty exciting. I'm going to be talking about the first fraction of a second after the Big Bang.
You mentioned 4 problems. What sort of problems are those?
The easiest one to understand is that everything we know about the laws of physics say that for every kind of matter in the universe, there exists an equal and opposite thing we call antimatter. The electron, for example, has a positive version of itself called the positron. And all the things we know about physics say that matter and antimatter can only be created together, and they can only be destroyed together. So the early universe, we think, should have had equal amounts of matter and antimatter. But if that were true, then these substances would have destroyed each other in the first fraction of a second, leaving our universe without any electrons or protons or neutrons, and therefore no stars, no planets, no life.
And we wouldn't be here to ask the question.
And yet we are. Somehow, something must have happened in that first fraction of a second that was very different than our current understanding of physics tells us it should have been, and that made us all possible. So that's the first puzzle. The second puzzle has to do not with atoms and ordinary forms of matter, but this other kind of matter that we call dark matter. We know it's there, we can feel its gravity. It makes up 5/6 of all matter in the universe, and yet we don't know what it is. We know it was formed in the early universe, shortly after the Big Bang, but we don't know how and we don't know why. The third puzzle is what we call dark energy. It's driving our universe to expand not at the same rate it used to be, but faster. It's accelerating the rate of expansion, making our universe grow faster than our theories would have otherwise predicted. Again, we don't know why it's there. We certainly don't know why it exists in the kind of quantities it does. Total mystery. And then the fourth and final of the puzzles I'll talk about is the puzzle of cosmic inflation. When we look at our universe as far away as we can and far back in time as we can, and I look in this direction and then I look in this direction, I see essentially the same thing. Our universe is remarkably uniform. And yet that part of the distant universe and that part were never in contact, so we don't understand how they could have become so much alike. What inflation posits is that the universe, shortly after the Big Bang, exploded in growth, kind of had a burst of expansion, and it took all those points that were in contact with each other and spread them out, so that now when we're looking over there and over there, we think we're seeing parts of the universe that are never in contact, but before inflation they were. So when I look at these puzzles, things that we don't understand, we don't know how to make sense of yet, we certainly don't know the details of, it makes me think that since they all point to that first fraction of a second, maybe we're thinking about that period of time wrong. I don't have the answer, but I think it begs the question of what about our universe's beginning are we really getting wrong?
So in your day job, you're head of theoretical astrophysics at Fermi Lab.
That's right, yeah.
Near Chicago. So how does what you do day to day feed into these 4 mysteries you've just talked about? I guess we should try and visit them each in turn. I don't know, do you have a favourite one that you'd like to start
dark
with?
matter is kind of my thing. That's what I spend most of my time thinking about. At its foundation, the problem is that when we look out into the universe, we can weigh things like galaxies. And when we do, we get a number that's 6 times too big. If it was only stars and planets and gas and dust that were present in galaxies, they just shouldn't move the way they do. The stars in the outskirts of galaxies zip around them as if there's a whole bunch of mass here, and that mass just isn't made of anything we know. Whatever the dark matter is, and we don't know what it is, but whatever it is isn't something that appreciably radiates, reflects, or absorbs light, something that, frankly, we don't see with our telescopes. Now, if you asked me 10 years ago, I would have told you, we don't know for sure, but probably the dark matter is made of these things called WIMPs, weakly interacting massive particles. And then I would have gone on to say, and we know how to find WIMPs. In order to be produced in the Big Bang in the right quantities, WIMPs have to interact a certain amount, and we know how to build experiments that can see particles like that. So we'd go to deep underground laboratories, we'd build these highly sensitive dark matter detectors, and I would tell you that in the years ahead, we're going to find these particles. Now, moving back to the present day, we've done those experiments, or at least a lot of them. They've worked. They've been very successful. No one's at all claiming that the experimentalists who built these things didn't do a spectacular job. They did, but we don't see any dark matter. This is making me think, well, maybe WIMPs aren't the right answer, or maybe WIMPs with some extra features that make them harder to detect, things like this, or maybe something played out in the first fraction of a second when we thought the WIMPs were being produced that makes them be produced in different ways. Different kinds of particles would emerge from that environment than we had naively guessed. So maybe there still are something like WIMPs, and maybe they emerge in a similar way, but we'd be missing part of the story if that's right.
Haven't we ruled out the best ideas? You were talking about these weakly interacting massive particles. Surely we would have found them if we've made these detectors specially to find them.
I would agree with you except for the word surely. Okay, so I think most of the theories we wrote down that described WIMPs have been tested now. That's probably fair to say. Maybe 75% of my theory papers from that era are ruled out now, but 25% aren't. But a lot of those will be tested in the years and decade ahead. So I still think there's a chance the answer will turn out to be WIMPs, but I also think it's fair to be wondering whether WIMPs are maybe not the right idea now. I think that's a fair question to be asking.
And what are some of those other ideas that...
My favorite other idea is that the dark matter might be part of what we call a hidden sector. Okay?
Sounds good.
Yep. So imagine there's not just one kind of particle that makes up the dark matter, but that exists, and then it has a whole bunch of other kinds of particles that it interacts with. There are new forces that communicate those particles among themselves in interactions, and none of those particles interact in any appreciable way with any of the particles we know about. So maybe in the early universe, all this stuff was present in a large abundance, and the dark matter particles interact with each other, destroying most of their abundance and leaving a little bit behind. And then the lightest stuff, the remaining stuff in that hidden sector slowly decays away. And that would be a sort of scenario we would have no ability to test today yet, but that would entirely explain how the dark matter came to be and why it's so hard to observe.
So dark matter, then, that's one of our 4 original problems. But we didn't go number 1, which was matter, antimatter.
Oh, yeah.
So what's the solution there? Because that must be the biggest thing. Hey, why are we all here?
So back in the 1960s, a Soviet physicist named Andrei Sakharov, worked out the conditions that any theory that can solve this problem would have to satisfy. There would have to be some process in nature that changes the net number of protons and neutrons, or net number of quarks, if you like.
Protons and neutrons being the thing that make up the bulk of matter.
That's right. And we call this a baryon number violating process. Never observed one, but Sakharov says that you can't solve this problem unless something does that. A second condition is that the interactions that do that sort of thing have to do it preferentially in one direction. Because if you had interactions that went both ways that changed the net number of quarks, some of those processes would make you more quarks and some would make you less, and it would all wash out in the beginning. So there has to be kind of a weighing of the scales in favor of matter over antimatter. So that's the second condition. And then there's a third condition, which says all of this has to be in play during a particularly volatile transition or series of events. Maybe the early universe had a sudden phase transition where these processes went into play, or maybe there was some sort of heavy particle species that fell out of equilibrium, stopped interacting with the stuff around it, sat around for a while, and then that stuff decayed or interacted in a way that made the matter at the expense of antimatter, like something like that. And we have lots of theories that do this. Most particle cosmologists like myself have at some point written a paper proposing a theory to do this. I wrote one some years ago. And the problem is we don't know which one's right. We have a lot of guesses, kind of like dark matter, and very little in the way of our ability to test those hypotheses.
How do we find answers there?
The Large Hadron Collider is a help to some extent. Some of the theories that say all this happened at a relatively low energy scale within the reach of the LHC, we're putting to the test. And slowly, we're ruling out otherwise viable hypotheses. Maybe if we're lucky in the high luminosity run of the LHC in the next decade or something, we'll confirm one of these. But at this time, we're really just able to test a small fraction of the overall list of models. The Large Hadron Collider tells us what our universe was like, or at least what the laws of physics were like a trillionth of a second after the Big Bang. I want to know what it was like 1,000 or 1,000,000 or 1,000,000,000 times before that. And to do that, we need to keep pushing forward to higher energies, which right now with our current technology probably means bigger accelerators.
So, third problem, dark energy.
Dark energy, yeah.
Now, dark energy's only really been around on the cosmic stage for a couple of decades, right?
That's
Can
right.
you explain something about that?
So, dark energy has a long history. We didn't call it dark energy, but something that's basically the same thing has a long history. When Einstein started to think about the cosmological implications of his theory of general relativity, he found that the equation said that space should either be expanding or contracting. And he didn't like that. He said, no, the universe really has to be static. That doesn't make any sense to him. He had some sort of deep philosophical objection.
Was that purely because that's what most people thought at the time, or?
Einstein, generally speaking, wasn't one to care what most people thought, but in this case maybe, and frankly I've never been able to understand this objection. He added to his equations a new term. It's put in by hand, and it's mathematically consistent. It's a sort of term you can add without destroying the theory, but we had no reason to have it there otherwise. And if you picked the right size for that term, made it exactly big enough, you could have a universe that was filled with matter that wouldn't be expanding or contracting. This was a universe that was fondly called Einstein's world. And then other people pointed out that that universe was really unstable. Places with a little bit more matter than others would start to contract, and other places would start to expand. So it wasn't really a solution. And then ultimately Edwin Hubble in 1929 showed us the space is expanding, and Einstein threw out that term and went back to his original versions of his equations. And then for the rest of the century, astronomers went out trying to find out whether our universe is one that's expanding now and eventually will contract, or if it's going to expand forever, just slowing down as time goes on. And in the 90s, we got good enough at measuring this to really answer the question, and we didn't get either of those answers. What we got instead was a universe that had gotten bigger for a while and then started to get bigger faster, started to accelerate. And nothing about Einstein's equations allow that to happen. But if you reintroduce that special term that Einstein had put in to make his universe static, you change the coefficient, you make it a different size, but the same kind of term, you can do that. You can make that upturn in the expansion rate. You can cause space to expand at an accelerated rate with such a term. So these days we call that term dark energy. And all it means is that every cubic meter of space at all times and all places in cosmic history has built into it a certain density of energy. In addition to any particles or light or anything, if you took everything out of it, it would still contain that fixed energy. And as the universe expands, everything else gets diluted by that expansion, but not the dark energy. The dark energy just keeps growing, and eventually that causes the universe to grow faster and faster. We don't know why it's there. We certainly don't know why it's there in the quantity it is. When we do a naive calculation, we get an answer that's wrong by 10 to the 120. Yes, that's an enormous number we're wrong by. It means we don't conceptually know what we're doing. So we have no clue why the universe is the way it is in this respect.
And this is an even bigger problem than dark matter, right?
It makes up about 70% of the energy density in the universe today.
Dark
matter
does.
Dark matter is a smaller piece. And whereas I can imagine answers to the dark matter problem, I can hypothesize a theory that might one day be shown to be correct. Dark energy, we don't even have any good guesses.
We do have guesses though? Or?
Well, let me tell you about one guess. It's actually kind of a good guess. It was posited by the great physicist Steven Weinberg back in 1987. He said, let's imagine that there's not just one universe. There's a lot of universes. Maybe even an infinite number, but at least a very, very, very large number. And in most of those universes, there's 10 to the 120 times more dark energy than in ours. Like that's the right calculation. But in those, the universe expands so fast that you never form things like stars, planets, or galaxies, and there's no life as a result in those. And then in a few of the universes, there's only 10 to the 119 times too much dark energy, and there's no life in those either. There's even fewer with 10 to the 118 times, et cetera, et cetera, et cetera. So if you follow this all the way down, it predicts that the vast majority of living things will find themselves living in a universe with approximately the maximum amount of dark energy that's consistent with life. That's about what we find ourselves living in. So maybe our understanding of the laws of physics are right if we take them into account the fact that we live in a vast, vast, vast multiverse. That's probably our best theory for dark energy, and it's a pretty wild one.
So to explain our own universe, we have to propose how
A
many
vast
universes?
number. I don't even know how to count them.
Okay, so we've got our fourth big question about
Inflation.
the first instance of the universe, inflation. How is that even possible? Doesn't relativity say nothing can go faster than the speed of light?
What Einstein taught us, or showed us with relativity, is that nothing can move through space faster than the speed of light. It doesn't say anything about what space can do. So, in fact, we can find places in our universe today that are moving away from us faster than light. We can't see them because light can't reach us from them. But if we look back far enough, we see what we call a cosmic horizon, which everything on that horizon is moving away from us so fast that light can't reach us. So we're kind of surrounded, all points in the universe are surrounded by a horizon beyond which we can't see or interact with. So we're not speculating or doing anything too wild by saying that space could grow faster than light. But inflation is a pretty extreme version of this. It posits that there's this tiny little window of time in the very early universe, maybe 10 to the minus 32 seconds or something, where everything got gigantically separated from each other. It would have been driven by something kind of like dark energy, but with a much greater amount of energy stored in it. And then it would come to an end, and that energy would be transferred into an array of particles or heat or energy, starting off kind of the early universe as we know it. That would leave the universe in a state where the part of the universe I can see in my distant telescopes this way should look more or less like the part I see over there. Without something like inflation, we don't know how to explain that.
Okay, and how do we explain inflation then?
That's a great question. Again, we have a lot of theories, and we're trying to test them with a number of different observations. So the best way we have at the moment is to study the cosmic microwave background with more precision. In particular, there's this quantity called the tensor to scalar ratio, which is something you can measure in this light left over from the Big Bang. Many inflationary theories, not all, but many predict a measurable scalar to tensor to scalar ratio. And experiments like the South Pole Telescope and eventually what we call the stage 4 CMB experiments might be able to see that. If we were to measure that, it would really narrow down the range of models or theories that can explain inflation. We're also looking for something called non-Gaussianities in the temperature distribution. And we're also trying to measure things like the tilt of the primordial power spectrum, all these sorts of things. I will say that when inflation was first proposed, it made some predictions that have turned out to be true. Those temperature patterns on the sky follow the sorts of features that inflation predicted. And I think at this point, it's fair to say that inflation has some real empirical successes. It has predicted enough things correctly to convince most cosmologists that something like inflation probably happened.
So those are our four big questions or unsolved problems. Which of them do you think is most, let's look in a timescale of 10 years.
Okay.
Which do you think is most likely, or maybe more than one,
Well,
likely to
if
be
I'm
solved?
right about the gamma rays from the galactic center being from dark matter, and I'm not certain I am yet, but I think it's reasonably likely. Then in the years ahead, we're going to see similar gamma rays from other places in the sky, in particular from dwarf galaxies. That would confirm that hypothesis. I think it would convince the bulk of my colleagues that it's true. And then we would probably devote more resources towards some of the other experiments, like the underground experiments, trying to measure this stuff. Maybe we would find ways in particle accelerators to study this sort of phenomena. I don't know. But over the years to come, we could really learn what the dark matter was. Maybe when we measure all the characteristics of the dark matter, we'd be able to reconstruct how it would have behaved in the early universe, providing us with a consistent or coherent picture for how it was created. Or maybe not, and we'll have to change something about how we think about the early universe itself. That's an exciting possibility as well. In most theories of dark matter that have the sort of particles that could make this gamma ray signal, those particles were formed between the first millionth and several millionths of a second after the Big Bang. So this would provide us with a way of studying the universe many millions of times earlier than we currently do. So in this sense, dark matter is a really important probe of the early universe.
Great. That sounds as good a place as any to end on. Dan Hooper, thank you very much.
This was great.
We should say that you've also written a book about all these things.
We should probably name drop that. Yeah, I've written this book, At the Edge of Time, Exploring Our Universe's First Seconds. All the things we talked about in this conversation are covered in there, and a bunch of other stuff as well.
Great. Well, thank you very much for your time, Dan. It's been a pleasure talking.